Hello everyone, I'm Madhuri. I'm a PhD student in ECE. In this talk, I'll introduce nonparametric estimation techniques and demonstrate their one application. A nonparametric technique does not assume any underlying distribution of the sample points. Instead, it estimates the density function by observing samples in proximity. If we don't know anything about the data at hand, then these algorithms can give us important clues about the data distribution, and then we can apply a parametric technique to get a better estimate. Furthermore, these techniques work even if the data doesn't follow a standard distribution. For example, most standard distributions are unimodal, while data can be bimodal. These algorithms provide generality as we can apply the same algorithm for any set of samples. Two famous algorithms in literature are Poisson window and K nearest neighbor, which we'll discuss next. Here, our goal is to estimate the unknown density P of x from n independently sampled data points from some unknown distribution. Suppose these are our n data points collected. Then, probability that k of these points fall in region R will follow the binomial distribution, and it is given by this expression, where the p is the probability that the random variable falls in region R. The maximum likelihood estimate for p is kn over n, and analytically it is given by the integration of PDF p of x over R. Let this R region has volume Vn and assume that this volume is so small that p of x is constant within it. Then this integration will be just a multiplication of Pnx with Vn. And if we equate these equations, then we will get the Pnx is equal to Kn over nVn. This will be our estimate of p of x from n samples, and it will converge if Vn becomes 0 and Kn becomes infinite as n becomes infinite. Also at infinity if samples in region R are just a fraction of the total samples. There are two ways to achieve these conditions, and these two ways lead to our two methods, Poisson window and K nearest neighbor. First way is to shrink volume Vn as a function of n, say Vn is equal to 1 upon square root of n. This method is known as Poisson window or kernel density estimation. Here we take a kernel which is defined as this. It is a rectangular function in d dimension. Then this summation will give the number of points in the hypercube of length hn around the sample x, and it will estimate our kn value, and then our probability density estimate will be this kn over nvn. Here we are not limited to the rectangular kernel. We can have any kernel as long as it follows these conditions. First condition is the positivity of w, and the second condition, the integration of w over r should equal to 1. These conditions will ensure that the r estimate is a valid PDF. Let's see convergence for this method. We say Pnx converge to the Px if mean of estimator is the true PDF and variance becomes 0 as n becomes infinity. We can give expectation of r estimator and variance by these expressions. We can see that if v volume shrinks to 0, then this function will be the delta function, and this integral will be the convolution of delta function and true PDF, and it will give us true PDF as the expectation of our estimator. And the upper bound of variance will be given by this expression. So if nvn tends to infinity, as n goes infinity, then the upper bound will be 0 and variance will be 0. Hence, as n tends to infinity and if volume V goes to 0 and NVN goes to infinity, these two values converge, and our estimate will converge to the true PDF. Note that here we have to select the hyperparameter Vn, and performance of the method will depend on it. If Vn is large, then the estimate will be smooth and we will have only a space average estimate of Px. If we keep V1 small, then estimate will have a large variance, hence the estimate will be noisy. We have to decide the trade-off, and moreover, the good value of V1 can vary region-wise. One solution to solve the problem is to make the volume Vn data dependent. We can grow volume until it can contain Kn samples. This is the K nearest neighbor rule. Here, expectation and variance can be given with these expressions. We can see that as n becomes large, the expectation will achieve the true value P of x, and variance will become 0 under the condition of Kn goes to infinity and ratio Kn over n goes to 0 as n tends to infinity. Hence, the choice of Kn as square root of n is good for this rule. Here we can see that Vn is also 1 upon p of x into square root of n. So in this method also, the volume shrinks as n grows. If we compare the variance over here and the variance with the Poisson window, we can see that Knn method has higher variance as compared to the Poisson window. Now, suppose we have these n points sampled from n classes, and we want to know the posterior distribution of each class. It can be given with the base law. Now suppose we form a volume Vn around our test sample x, which contains k samples, and then we count the samples which belong to the class Wi. Let's say this count is ki. Then density estimation of p of x and Wi is ki over nVn. So we get posterior probability as simply ki over k. Here we simply select the k nearest neighbor of the test sample and assign it to the class which offers maximum number of times. This is the famous k nearest neighbor classifier. The error rate here is lower bounded by the base error and upper bounded by twice of that. Here I perform some simulations with a Troy training data. The data is sampled from the normal distribution of zero mean and unit variance. estimated the true distribution using increasing number of samples and various weight. I use the Gaussian window as a kernel function. Here we can see that for smaller edge, the estimate has noisy spikes, and it gets smoother as edge increases. Furthermore, the estimate gets better as n increases. A point to be noted that the effect of edge is negligible around huge n because these estimates are almost similar. Here I use the toy training data with KNN method, and k is taken as square root of n. Here we see the same pattern. As n increases, the estimate gets better, and even though the estimate is continuous, there are discontinuities in the slope of the curve. If we compare the results of Parsons window and KNN for large n, then it is evident that KNN has higher weightiness. Nonetheless, it gives a good estimate without having to worry about the window width parameter. Here, I implemented the KNN classifier that estimates the posterior probabilities of all classes for each test image. It selects the class which gives the maximum posterior probability. The training data here consists of 5 classes: buildings, trees, mountains, cars, and beaches. There are 20 training and 5 test images for each class. Each image contains approximately 10 to the power 4 pixels. Hence, directly applying KNN to this data would be computationally expensive, both in terms of time and space. Hence, we first should extract features which can maintain the variability among classes and have fewer dimensions. Here we apply the local binary pattern histogram method, or LBP. The LBP method forms 8-dimensional feature vector depending on the grade level changes in the image. This is a huge cut in the computational cost. Here we use the confusion matrix as a performance metric, where row represents the true label and column represents the predicted label. If a true label and predicted label form a pair ij, then the count at position ij in the matrix is incremented by 1. By this structure, for an accurate classifier, we should have maximum values on the diagonal of the confusion matrix, and off-diagonal elements are misclassification. The overall accuracy of the classifier is computed as the percentage of points on the diagonal over the total number of points. From the confusion matrix, it is evident that the classifier is confused between mountain and buildings. This is because mountain and buildings have similar vertical features, and their feature vectors are also showing the similarity. Hence, the LBP feature vectors might not be sufficient for this data. Few misclassifications can be attributed to insufficient training data. We can see here in the second diagram of k versus overall accuracy, there is no much change in the accuracy as we increase k. This is due to limited training data. Hence, if we have a large training data and good feature vectors representing the various attributes of classes, then considering a sufficiently large k would give us more reliable label. Here, training time required for this data is around 1 hour, and if we save the features in the memory, it can save a lot of time. However, the memory space likely to grow as we include more features. Also, during the inference, we have to compute distance between test sample and each training data, which will be computationally expensive as training data increases. Here, we learned the basic framework for the nonparametric estimation, and we analyzed statistical properties of Parsons window and KNN method, and we saw their application for image classification. We found that nonparametric techniques are good when we don't have any knowledge about the underlying random process. However, these methods are data hungry and require huge training data for optimal performance. Thank you for listening.